Hello, am I audible?
Sir, it's audible, sir.
Okay. Shall I start?
Yes, sir, you can start, sir. There is internet connection for Ravi Kumar, sir. He told me to start.
Okay. There is this panel on the right-hand side which is blocking my view. How do I? Okay. Okay, I understood. Okay. Hello everybody. I am Dileep Menezes. Hello, is my screen
It's
seen?
visible, sir. Visible, visible.
Visible.
Yes, sir,
Okay.
it's
So I'm
visible.
the managing director of 3D Systems India, and I'm here to give a talk on emerging trends in the 3D printing. So just to understand, do I take the questions in between or do I keep the questions for the end?
So at the end of the session, the questions will post and they will ask you the questions, sir.
Okay, okay, excellent, fine. So just a couple of slides about my company. This is a man called Chuck Hull, and he's the father of 3D printing. So he basically invented 3D printing in the year 1983. This is the first part that was ever printed. It's a cup, and it is still there actually. This is one of the first 3D printers, and this is Chuck Hull now receiving one of the many lifetime achievement awards which he has got over these years. Now, not many people know this, but Chuck Hull is the person who started 3D Systems. That's the company. That's the company which I work for. So when it comes to legacy, we have the longest legacy in the industry. That's because our founder actually invented the entire concept of 3D printing and then started the industry. Another slide about our company. So we were founded in 1986, and we have around 2,600 employees worldwide. We are available in 68 countries, either directly or indirectly through our channel partners. We have 13 offices, and we have around 1,000 plus global patents. So there was a time wherein we had more patents than employees, but ever since we have scaled up, the employees have become more. We are headquartered in Rock Hills, South Carolina, in the US. So these are the main industries that we cater to. Healthcare is one. So there's dental, although dental and healthcare fall under the same thing, but the dental solutions are very different. So that's a separate vertical according to us. Aerospace, automotive, and also durable goods. These are the major verticals. However, there are other smaller industries like jewelry, jigs and fixtures, and casting, which can go across these industries and play an important role as well. So my talk is basically about the emerging trends. But before I get to that, I want to just show you a few parts that have been 3D printed. Okay, this is a buckle. This is a vent of an automotive car. This is a full color model of a tool. This is a 3D printed module of an engine, a manifold. This is a full color model of a shoe, and this is of a rubber part. Okay, it's flexible. This is a metal print of dental prosthesis. In this image, you see three things. This is a wax printed part, and this is the casting made out of the wax printed part. This is also the wax part, and this is the casting made out of it. This is a medical implant. It's a spinal cage actually. And this is a metal part which shows you of a fuel injector, and it's a section which shows you how intricate it is. This is also an SLA part of a casting. So basically, it's a pattern used for casting. Now, the reason why I'm showing you this is because over this week, you are going to learn a lot of things about 3D printing, different processes, different ways to print, STL files, CAD models, and everything else. What I need you to keep in mind that there is a difference in the end use, and there is prototyping versus the production. This line here, towards the left of it, these are prints which are used in the prototyping stage, and on this side are all parts used in production stage. When I mean production, meaning this is not a prototype anymore. This is actually used in a machine or in a human body or as jewelry. So these are parts which are used in the production stage. So the number of these parts that you will print is huge, is a large number. It can be from 10 to 20 to 50, 100, even thousands. On this side, you will see prototyping. So maybe you'll print 4 or 5 of these because you are still prototyping it. And eventually you will use maybe plastic injection molding or say vacuum casting to actually make these parts in bulk. Okay, so this is something that you have to keep in mind. This is something that you have to keep at the back of your mind, and then you will understand where I'm going with when I get to the slides um, about the emerging trends. Okay, so there are 4 emerging trends which I'm going to talk about over the next 1 hour. One is so how 3D printing is being used to maybe do the part of vacuum casting, maybe do some part of injection molding, maybe do some part of medical implants, which is turning out to be a far more interesting way of making implants now, and I'll explain why. Also, assembly consolidation. This is a term used to, if you have a very complicated assembly of parts, do you really need to have that assembly of say 5, 10, say 20 parts? So can you re-engineer the whole part so that it is just 1 or 2 parts, and then you use the benefit of 3D printing? So these are the emerging trends. I will tackle both these in one set of slides, and then have separate slides for the implants and the consolidation. So let's talk about the traditional manufacturing. So this is more on the plastic side of the business. So if you look at this graph, on the y-axis you have the unit cost. That's the cost to print a single part. And on the x-axis you have got the quantity. So if you see orange, injection molding, the curve goes like this. Why? Because if you have to print just a few parts, the cost per part is very huge. Why? Because you have to make the mold, and you have to machine the mold. That takes a few weeks and then costs, maybe thousands of lakhs of rupees. So if you want to if you want to manufacture just say 20 parts, then the cost per part is going to be very expensive. But as the quantities go higher, then the cost per part drops down. So injection molding makes sense when you have to manufacture a large number of parts. There are sometimes you need a lesser number of parts, and injection molding may not make any sense. So you use vacuum casting. So vacuum casting is not a process which can be used very effectively to manufacture thousands of lakhs of parts. It is for smaller numbers. So if you see in blue, this line is completely horizontal. It's flat. Why? Because the cost per part for 3D printing doesn't depend on the quantity. You have a printer, you have the material, there's a fixed cost that you assign for one part, and that part comprises of, that part cost comprises of the cost of the material and cost of the printer over time. So it's basically a fixed cost. So if you see this, so 3D printing completely is able to replace vacuum casting. So the the rule of thumb is that whenever you have an application wherein you have been using vacuum casting to manufacture a few parts, that can now be completely overtaken or overrun by 3D printing. If you see, this also spills over to the injection molding side. So that's also true. Over some part of injection molding, it still makes sense, and I'll explain why. Because although the cost of the injection molded part is lower, and the cost per part of 3D printing is higher, but there are some instances wherein it still makes sense to use a 3D printing. Okay, and as I go through the presentation, you'll understand why. So let's talk about production, how it happened in the past. Uh, so this is an SLS printer, and this was done in the year 2010. We wanted 1,000 parts, and we were able to print it. So this is an example of how we used 3D printing for production about a decade ago. Now, what you don't see here is the cost per part. I mean, the cost per part was quite expensive, but there was a need because these parts were actually required urgently. So that is why it was done. So it took 18. So if you filled up the platform completely and made all these parts, this is the amount of time it took to print per part, which is extremely small. Here is another example using the SLA technology. Now, all these terms, SLA, SLS, DMP, are something you will learn what they are over this week. But this is another kind of a technology. In 7 odd years ago, we wanted 640 of these parts. And as you can see, we completely optimized the platform. We put one part into the other and then actually printed it to a point wherein it took just over a minute per part. Okay. Again, here it was an urgent need, so we had to print it. This is another example of an automotive part. So bridge manufacturing is a term used in the industry when you need to have parts urgently made as a bridge to the traditional way of manufacturing. So this was an automotive part. There was a last minute change in the design, and until the tooling could be made, there was an urgent need to actually release the car. So we went and printed all these parts, and that's how it was done. And then after, so we came to know that it's not economical to print, but due to the time constraint, that's the decision that we did. Now I will come back to these 3 slides later on because I want to show you an emerging trend that is coming, which is going against all this logic now. So I want to introduce you to one of our printers. We have an entire range, but this one is important because this shows the trend. This is called a figure for modular. Okay, it's a different kind of a printer. It's not just one printer with one platform and then you print some parts on it. It basically has a controller, and there are modules. One module each. Each module can have a different material and can print a different part. Now, this controller can control up to 24 modules. What this means is you can basically set this up as a small factory. Okay, this is the build volume, and the thing to be noted here is the print speed. We can print about 100 per hour, which is very fast. In the 3D printing world, this is a very fast kind of a speed. You can see with this kind of a printer, you can print about 10,000 parts per month. Okay, and the material is fed completely automatically, and the curing is done in basically minutes. So this uses a resin, and it is cured using a UV light. And as you can see from the pictures here, there are no visible lines at all. If you've seen maybe an FDM printer which you'll have made in your lab, you will find lines, right? Those are the build lines. Now you will see that if you put load on that part and stress it in all kinds of ways, there are weaknesses in the part along those lines. Okay, because they're built in layers. So although it is fused, still the material properties are not isotropic. Isotropic meaning whichever way you orient it, the material properties will be the same. So, but if you see here, this is the kind of surface finish and the detail that can be got with this printer. And in the next slides, you'll understand why this is important in terms of manufacturing. Another important thing is the material. So One thing that happened all over these years was that there were some printers that could print very fast and could print in large volumes, but the material that was used by them to print didn't lend itself well to a production environment. Say example, if you take a resin and you cure it to form a part, that part is then exposed to UV light that's in ambient. So there is obviously sunlight on it. So over time, these parts they get overcured and then they turn hard and brittle. So although this was good for prototyping, if you use it in a production environment, sometimes it wasn't good. So we as a company have now come up with materials which have long-term environmental stability, like 5 years or so. Okay, there's also this particular material called the Pro Black 10 has got very good mechanical properties as well. So the HDT is quite high. It means that it can be kept in the sun. It won't deform. It won't it won't break. It won't turn brittle, and it's got a good elongation at break as well. If you see this picture here, before the part snapped, so it was pulled from either side. Before the part snapped, it actually necked. So necking is when the part turns smaller and then it breaks. This is a very good property of thermoplastics, which this material now has. All other printers, all other previous materials that we had didn't have this kind of a property. So what has happened over the years now is that the printing process has changed. The part quality is turned excellent. The print speed has also decreased a lot. And now we have good production grade properties which can be used parts like these automotive parts. So this material is good for motor housings, connectors, snap fits, and stuff like that. So let me give you an example. Let me run you actually through an example. This is an automotive part. Now, this part was actually an assembly of 4 or 5 parts. This is a part used next to the windshield washer. So to give an idea, uh, a zip tie goes in here and comes out from here. There is a washer put here and a bolt goes through to actually secure the part. And here is a sensor. This is what it is. This has been re-engineered now. Now, any of you, uh, if you have got some experience in injection molding, you'll soon look at the design and see, okay, this part cannot be made using injection molding. How are you going to make the mold? Where is going to how are you going to where actually will be the parting line? How are you going to maintain all these channels? Okay, so this shows the benefit of 3D printing in the sense that you can now come up with designs which can be printable and which cannot be made in any other manufacturing technology that is there right now. So will use this as a nice example to show what the emerging trends in the market now are. And this is what you should start to think when you go through this course and also do your research. Don't just think of taking parts that are already made in traditional ways and printing them. That is solving half of the problem. The more interesting half of the problem to solve is looking at a part, looking at the design, identifying the design intent, what it is exactly that this part is supposed to do, and then thinking, okay, can I redesign it to do this in a better way? Can I make it less complicated, which means less expensive to manufacture? Can I make it more efficient? You know, my screen sharing is paused. I just got a message. Can you all hear me? Can you all see my screen?
Sir, sir.
Yes? Okay.
Yes,
Yes,
sir, we
yes.
are able to see, sir.
Okay, I'll continue. Um, yes, so you have to ask all these questions. This is the real value add that you'll get from a course like this. So let's use this example and go through the entire process of actually 3D printing these two parts. It's a pair actually. Okay. So this is how we basically set up the build. So this is the build volume. and we have done vertical stacking, and we have like nested the parts to such an extent that we have used almost all the space. Now you have to understand this is a production application. Okay, so let me give you an idea. We needed thousands of these parts to give as handouts at Formnext. Now Formnext is the world's largest 3D printing exhibition in Germany, and last year we wanted to print thousands of these parts. Okay, so we had to basically assume that this was a manufacturing application. Okay, so this is not prototyping anymore. You just don't want to print one part, you want to print thousands of them. So you have to think differently. You have to set up the your printer in a way to optimize everything. And I'll just play a video. Maybe you'll not hear the sound, but it's only music. But it's a time spared video. So you can see 2 hours here. So so in about five hours, we have printed 120 parts. So it comes to 2.5 minutes per part. Okay. Now, remember what I said earlier about the cost per part, right? Using the older ways of SLA, SLS, the cost was extremely expensive, but then it was important to do it because it was a time critical thing. So they said, okay, let's spend some more money, but print these parts instead of waiting for the tool. But now look at these prices. This is a design which you cannot make by injection molding, okay? And it costs only $2 per part. This part cost 62 cents. This is amazing. And this is the emerging trend that we see in the market right now, which is being adopted in the US and in Europe. So the Figure 4 modular is being acquired by a wide variety of companies as we speak, and they are seeing the benefit of this, and they are seeing that they can completely change their designs and print parts which they could not manufacture. Okay, now this is what happened after 24 hours. These are the number of parts that we got. As you can see, it's lots. This was after 48 hours. So basically, we had to put all these parts in one big box and ship them from our San Diego office where these were printed to Germany, and then we used to hand it out to everyone who came at our booth. This tells you that now 3D printing with the right printer, with the right material, and maybe the right design as well, can be used for manufacturing, and it is economical, it is better, and it is much more cost efficient as well. uh, they say the proof of the pudding is in the eating. So here is an example. This is basically the picture of the Figure 4, and you see this part over here that's actually blown up. This part is actually printed on the Figure 4, uh, and we are saying why not? Because we just need maybe 500 to maybe 1,000 a year, because we just launched this printer. There's no need to make a mold to actually print this part, to actually manufacture this part by injection molding. So we just planned, let's just print these parts, and this is the design. Now here's the interesting thing. So in a batch of that takes 8 hours to 1 second 8 hours to print, we can print about say 12 parts. So it comes to 40 minutes per part, and that's okay. Why? Because we just need 500 to maybe 1,000 a year. So it's fine. But here's the interesting thing. This is a new product, right? So there can be times in which we may need to change the design all the time. So maybe this angle needs to be turned more, maybe this hole has to be got in front. So if we had a mold, we have to redo the mold the whole time. So that turns extremely expensive. There's also lead time. So here, quick design changes are possible if we print. Because if we say, okay, let's move this thing over here or change this angle to make it thicker, then that can be done the next day itself. You can prototype it and then directly print it. Maybe the part fails here. Maybe this rib maybe we have to have 2, 3 ribs over here. So we can immediately do that, and this enables us to have a just-in-time management for inventory. So you don't need to place an order with your supplier saying, okay, I want 500 of these parts, go and give it to me. Then your design say changes halfway. You go back to the guy and say, okay, I want this part in this color. Then he can give it to you in that color. So
Hello.
No audio, sir.
Hello, Dileep
Yeah, yeah,
sir.
yeah.
It's
Hello, Dileep sir. Hello.
sir. The hello, Ravikumar
Hello.
sir.
Yeah, yeah.
దిలీప్ సార్కి ఇంటర్నెట్ ప్రాబ్లం ఆఫ్లైన్ వెళ్ళిపోయాడు సార్. ఇప్పుడు వచ్చారు సార్ మళ్ళీ.
There may be some internet connection
ఓకే.
problem.
Hello.
Rakesh,
సార్ కృష్ణారాయణ సార్ చెప్పండి సార్. నేను
ఒకసారి ఏమైనా కాల్ చేస్తారా ఆయనకి?
నేను చేస్తున్నాను సార్.
yeah, can you hear me?
ఎస్ సార్. ఎస్ సార్. ఎస్ సార్.
Okay.
Carry on. Yeah.
I'll carry on, right? Okay, fine.
Yes.
So this is a case of a good example of assembly of assembly consolidation. You can save time and cost, which makes your company more competitive. Because if you have a product that is not selling well because it is outpriced out of the market, you can then use these technologies to get your cost down and then turn it successful. Now here's where these things can be very important for you guys. If you're a designer, you need to just you need to think about this thing for design for additive manufacturing. So just like how you design for injection molding or for casting, there are some rules, right? So you have to learn the rules for AM and try and adopt them in your practices, because you have a large, quantum of the design freedom. Of course, you can't print any and everything. There are some rules even for 3D printing, but they are not as restrictive as the rules for the other modes of manufacture. So if you're an OEM, you can look at your item that you make, your product, go into it and do a deep study. What are the possible candidates of parts and assemblies which I can adopt 3D printing for now, in terms of manufacturing, not just prototyping, because everybody uses the 3D printing now as a prototyping tool. That's quite common, but not many people are looking at it as an avenue for manufacturing. If you're a supplier, say if you are a company that does injection molding, you can offer a faster turnaround time to your customer. You can even offer a lesser cost, and then you can win more business. Because if you tell your customer, look, this is a part, you want 20 of these, but now I have to make a mold, so each part is going to cost you say 10,000. but then you print one and show him, look, this is a printed part. Does it work for you? You want just 20, right? And if he says, yes, it works for me, then then you can say, look, then now this is going to cost 2,500 rupees. Okay, so that way you can win more business. So then the next time the OEM wants to choose a supplier for his next need, he will obviously call you and say, look, last time you gave me an excellent product at an excellent quality and at a extremely low price. Can you do it again? And that's how you win more business. So these are the emerging trends that are there in the market which we are seeing. And it all starts with understanding where the line is between prototyping and production. So I've been talking about the figure for modular, but I just want to talk to you about the entire figure for product line. What we have is actually a standalone as well, which has got just one module, and there's no controller and there's no other stuff. Here, you pour the material manually in your hand, okay, and this is used for R&D purposes, like 200 parts a week. We expect that companies who have a figure for modular will always have a standalone, because this is where you do the experimentation, and then when you come to a part which can be produced in mass, that's when you come over here. Now, if you want to really scale up, print like 1,000,000 parts a year, then we have got something called as a figure for production as well, which is basically there are 4 print engines in each module here, and there are also robotic arms that come and pick and place parts, wash them, dry them, and it is completely insanely customizable and also automated. Okay, so this is where it is now. The next emerging trend that I would like to speak to you about is the use of 3D printed the technology for medical implants. So let me just walk you through the workflow first. The end product is this implant that you need for a patient. So first you first scan the patient, then you use a software. This is our product. It's called D2P, but you can use others as well, which takes the CT scan data, which is basically a black and white or grayscale 2D slice images, and convert into a mesh. Then after that, the next step is to use an organic modeling tool to actually design that implant. To help in the organic modeling, we also offer a haptic device, which is basically a touch-based thing. So it works like this. You hold this like a pen and you move it around in space. And wherever the cursor hits an object on the screen, you get a force feedback. So it's like sculpting. This is good because you cannot make a design like this in something like SolidWorks, because that uses lines and arcs, and a human being is not like made up of lines and arcs. Um, After that, after you make the implant, then you need to lightweight it. You need to make internal and external lattice structures, which really give you the benefit of 3D printing this. This is another software that we have called 3D Expert. Uh, in fact, you all have a license of this. So a license of 3D Expert comes along with DMP Flex 100, which is there in your lab. Then after you do the design of the implant, you use it, you actually print it in a 3D printer, and then you operate. This is basically the workflow. So this is the benefit of doing this by 3D printing. So you can make volumetric lattices like this way, and also surface lattices. You can parameterize them. So you can actually open a dialog box and choose the parameters of what should be the pitch and the angle and the number of nodes and the kind of design. Then choose the volume on your screen and say fill, and this whole thing will be automatically made. You can print it, then you can test it, and then if it is not good, then you can come back here and change the design, just a few clicks, and then you have a new lattice structure. Now, why do you need lattice structures? See, this is an implant. This is going to go into human body, and this is going to go and attach itself to one end of a bone. Now the bone needs to fuse with the implant. If it doesn't fuse well, then it will fail. it'll come loose, and then the patient will need to be operated again. So because you can print insane geometry like this way, that is why you have better osseointegration. So the bone will grow into it, like the roots of a tree. Even if there's a high storm, and the top of the tree is being pulled and pushed everywhere, but the roots are so ingrained inside the soil that the tree doesn't move anywhere, right? So that's same kind of a concept used here as well. Also, there may be cases wherein the bone needs to grow over an implant, because the implant needs to be really strong and solid, but the top of it needs to be very rough. Now the traditional way of making implants is by CNC machining. Now you can see this can't be machined; it's impossible, right? But using 3D printing and using the software that lends itself well to this kind of an exercise, you can actually come up with some really nice implants with a very low failure rate. So this is a slide explaining osteointegration. So this is a spinal cage made on a metal 3D printer, and this is used as a replacement. So this is a spine, and this cartilage kind of a thing was like removed here, and an implant was put in its place, and then you can see the bone that's growing completely into it. This is how osteointegration is done. This is another case of a canine implant. So this is an implant for a dog. So there's a condition where the lower limb of the dog is weak. So what they do is they slit the bone, yeah, and then they put this implant and they screw it here, 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 and here, and that's how they give this a thickness. This is a case of an implant done in Erode in Tamil Nadu. This is a live case actually. This was a very complicated case. As you can see, uh, there was cancerous kind of an element in the lower jaw and also in the top part of the jaw. So this one case needed the 3 implants, one for the lower part of the jaw, one on top right, and then the top left. And all this was done. So this white thing is also 3D printed. So we use the 3D prints of the bone to test the metal implants as well. And then finally, the operation was done, and it was a success. Now imagine if there was no 3D printing. What would happen was the doctor would have to use the CT scan, the data, look at the X-ray kind of images, and try and guess what would be the situation when he operated. And then he would have to open up the patient and then say, oh, I thought this was the case, but actually it is not. The case is a little bit more complicated. Then he would have to think on his feet, and he would have to then cut more and plan less and do all kinds of stuff. And then he would have to take pieces of, say, titanium and actually bang them into shape. So this is what actually happens in the OT. There are heavy metal tools which the doctors use like a blacksmith, and they hit pieces of titanium so that it gets shaped to suit the patient. There are some times wherein they have to modify the patient to suit the implant, and that is because they can't change their implant anymore because it's quite complicated. So all those things are all those variables are like taken care of by 3D printed implants. So the emerging trend now is that metal implants, titanium implants, are more and more being extensively used instead of the CNC ones. The fourth and last emerging trend which I want to talk to you about is the thing of assembly consolidation. Now, if you look at this is an automotive exhaust, okay? This comprises of 20 parts. And if you look at these parts, you can see that the person who designed this was already thinking about how he was going to manufacture it. He had certain manufacturing processes in mind, and that is how he had to take his idea of a full-blown exhaust and cut it up into parts so that it could be manufactured. Then what happened is we told the guy, okay, you have got complete design freedom now. Okay, you have to follow the rules of 3D printing, which will explain to you, but you make up your automotive exhaust completely as you like. And what he did is he reduced the 20 parts to one part, and this is the thing. This is completely made using 3D printing as one piece itself. It is the same job, but it's actually better because there was in the end 75% reduction in production time. So you can imagine how much time it'll take to make each one of these parts. You add them all up, time and resources, and here you then compare it to the amount of time it'll take to make just this one part. Okay, then you have to also add the assembly time, and then you have to check for errors because there's fitment errors, there's mating errors, there's all kinds of stuff, assembly errors. All that is not there here, but here everything comes out as a piece. This is an example. This is another example of a quartz glass burning tool. This was how it was earlier. This also had 20 parts. As you can see, there are joints everywhere. Now this was re-engineered to look like this. This is just one part, completely one part. There are it's exactly hollow inside, so that the gas can can uh, can flow through. Now 50% less material was used. There was a shortage in the production time as well, and it is 60% more cost effective. Over and above that, it lasts 3 times longer. So here's another example of how a part was there, an assembly was there, and somebody re-engineered it completely. So while you go through this course and through your additive manufacturing journey, don't take geometry that comes to you as something that is like set in stone. No, you're an engineer, okay? Your job is to think in a creative way. Just because somebody made something in certain ways, it doesn't mean that you have to do it in the same way as well. At that time, they didn't have 3D printers. They didn't have the processes. They didn't have the materials. They didn't have the technology to make things in a very different ways. So they were restricted to what they knew and what they could do. You are not. You have all these tools ahead with you now, and it's up to you to use them in a very effective way. Here is another example of a heat exchanger. This is a good example because this had 155 parts. As you can imagine, each of these things was one individual part. And here this was completely reduced to just one part. This is made only um, as a piece. There's also like reduction in the production time. There's also reduction in the volume. That means it is lighter, and also there's also like a 20% improvement in in also the performance. Okay, so I've intentionally left no text on this slide because so normally what I do is I ask the audience what this is, what they think it is. And now since I can't ask you, but I'll explain to you. This is a heat exchanger. Okay, look at the complexity here. This is like a cut section view, which shows you what kind of fluid flow is happening inside. So this is where the liquid comes in, is a spiral, and then it comes out. And the section inside has got a spiral inside of it, which effectively turns inside. So can you imagine the efficiency that is there in the heat exchange? And these are the fins. All this is just one part. This is actually just one part. In fact, this part was made on the Flex 100, which is what you have in your lab. So imagine you're an engineer now. You have to solve a huge problem, and you say, okay, I can now see if I can use the 3D printing to see if I can solve this problem, and you have complete freedom to use all the tools that you have at your disposal and come up with the solutions that absolutely nobody could have actually thought about. Okay. Uh, with that, I will end. This is my contact information, my phone number, email address. I mean, please, if you have any questions or anything you want to talk about, just drop me a line. I may not answer you immediately, but I will answer you because I think it's my job and my duty to keep a certain amount of time out of my schedule to respond to students, uh, because I think that if their answers, if their questions are not answered, then it's a big opportunity that we have actually lost. So please feel free to hit me up. I have around 10 minutes now, I believe. Mm, yes, but I think there's a quiz.
Yes.
I
Yes, sir.
I can stop sharing my screen so that you can.
No, sir. Before the Dileep sir.
Yes.
Yeah. Before the quiz. So if they are having some questions, then we can take quickly one or two questions, and then we'll
Yes,
move on to
sure.
the quiz part. Yeah.
Yeah, sure.
So, yeah.
I'm seeing some of the questions in the
Hello.
chat.
Correct. Yeah.
Yes.
Hello.
Yeah.
Yes, yes.
Doctor, sir, I have a question regarding this. So cross-processing of AM methods. So you have explained the various cases for metal 3D printed part. So what are the processes you follow for improving the surface quality?
So there are many. So one thing you have to understand is that when you do 3D printing of metal, okay, you are never
Yes,
going
sir.
to get as good as a surface finish as a machine part. Okay, so that
Yes,
is one thing you have to understand. You'll always get a
yes,
grainy kind of finish. You can
yes, sir.
orient the part in certain ways so that you can minimize that effect, but that effect will be always there. So if you are designing a part, let me see if I can so if you have got mating surfaces, okay, which need to be completely flat, like these two screens of my phones, okay, what you do in the design, you add stock, so you add extra material that you print, then you go
Okay.
for NC machining later. So this is called hybrid manufacturing. Okay. So then
Yes,
you
sir.
shave off that machine, shave off that much amount of material so that you end up with a part that is completely smooth. Uh, Another thing, if you need to have a hole, okay, you don't need to actually print the hole because there are times a bolt needs to go into it. It needs to be completely circular. You can actually defeature that part, so you can remove the hole in the design. You can print the part completely filled up, and then afterwards machine that. So it's on you. If the surface is to be like an NC machine kind of surface, then you can choose hybrid. Or if you don't want it that smooth, but looking good, then there are other ways like sandblasting is there. Then other things of say heat treatment
Yes.
also
So
can be used.
laser processing, laser surface processing can be used for
It can
this.
be. So there are many things like this, but it's on the application. So just because an
Uh,
option is there, you should use it.
Right, I have doubt regarding the bio implant. Say, just like in a hip implant or any other implant, in some cases the rough surface or texture surface can be useful for. So, so for what do you say about this the surface texture?
So yes, you are right. In fact, the rough nature of a metal printed part lends itself well to medical implants. However, there are some places in the body wherein a smooth implant is required, like the jaw. What they have found
Yes.
out is that jaw implants actually need something that is very smooth. So what we do
Yes.
there is we use like a Dremel or a hand tool and actually do the surfacing by hand, because you can't use an NC machine over there because it's an organic shape. So you can't really do that. So you need to understand the application, what is the actual need, and then use the process accordingly.
Yes, sir. Okay. Thank you, sir. Thank you so much.
Yeah, thank you for
Yes.
the question.
Hello.
Yes.
Good morning, sir. Sir, I wanted to ask that if, like, I'm a research scholar and my project is on metal 3D printing, but I don't have facilities at my center for creating the product. So, can you tell me the resources which I can use for like making the prototypes, metal
So
3D printed?
there's two ways to do it. One is so in the software like 3D Expert that I showed you, you can even
Yeah.
do a build simulation. So
Okay.
you can do you can import a design, you can add you can orient it properly, you can add
Hmm.
the supports and then do a build simulation. Okay. Once you do
Okay.
that, then you have the option to either send it to a printer or
Hmm.
send it to your printer if you have one, or you can give it to a service bureau which has got a printer, or maybe give it to a, a place like say NIT Warangal, and then you can print it. But you would basically use the build simulation a lot earlier, so that you know that the part that you print, you're almost certain that it will work, because
It will work.
these parts are very expensive. I mean, the printer is quite expensive, and then the cost of actually keeping it up also is quite high. So this is not like a normal FDM like printer where you can print, you know, two, three
Correct,
kind
correct.
of designs in one platform, and just
Experiment.
experiment will. So this is a proper capital good kind of a thing that's been invested. And actually your NIT Warangal, uh, like I said earlier in my opening remarks, the students here should, and also the faculty should consider themselves very lucky to be able to get access to something as complicated and advanced as a metal 3D printer. So I really hope that y'all make good use of it. And as part of industry, I mean, as part of the OEM, I'm also willing to work more closely along with NIT Warangal, and offer some assistance if required in terms of knowledge sharing or something of sort.
Sir, actually, I'm not from NIT Warangal. I'm from Amravati.
Okay,
So
okay.
we don't have any such facility over here. So there are not many what do you call that, organizations which deal in metal 3D printing. So that's why I was asking you.
Okay, okay. There are questions.
So,
Just,
a few questions in chat box. Let
yes,
me read out.
Yes. No,
yes,
no,
yes.
yeah. There are quite interesting questions are there in chat box 2, 3. Yeah.
What
Yeah.
software we used for modeling a part considering a lattice structure? Can we use the traditional CAD software for the same?
No, no. So some traditional CAD software now have got separate add-on modules which are catered towards 3D printing. So if you have that module, then yes. But traditional CAD software is tuned to making the base part, to just make a bracket or hub or flange somewhere that way. But they really don't deal with lattice structures and stuff like that. Although some of the CAD vendors are now coming up with modules for that, so you have to cross check with them.
Okay.
So our
One
software
more.
3D Expert has all those tools.
So, one more question, sir.
Yes.
What is the future of 3D printing in organ manufacturing for organ transplant?
Oh yes. So we also have a team that is working on bioprinting. We don't have a product yet, but hopefully it'll be out soon. So this is not science fiction anymore. Maybe 10 years back it was science fiction, because some guy came and showed that he printed a liver or pancreas. The problem back then was that yes, they could use a stem cells to print an organ, but that organ could not live. Why? Because they could not print the blood vessels that are needed to keep an organ alive. But over time now, things have changed. And now the research has gone to an extent wherein people are able to print the blood vessels and the capillaries, the veins and arteries, which go into the organ, and hence these organs can be kept alive. So if you ask me, 20 years from now or 10 years from now, you may not need to wait for an organ donor for you to get operated. There may not be a need, because you will use your own stem cells. They'll be cultured, it will be sent to a printer, and they will actually print an organ for you using your own body tissue. And that is not science fiction anymore. It is going to happen. In our lifetime it will happen. In your lifetime it will happen.
Okay, thank you. Then
Yes, I think we've reached the end of the time.
yes. So now I will post the quiz link, and you can the participant can attempt the quiz link. Thank you, Dileep sir.
Okay,
Thank you, sir.
you're welcome.